Hi, I'm Erik, a software engineer at Salsify, a commerce and content platform enabling brands to deliver product experiences across the digital shelf. Today, I'd like to take you through some of the tooling that has supercharged development at Salsify and made GraphQL one of my favorite technologies to use across the full stack of development. On the back end, I love how GraphQL allows me to express the resources the service provides in a natural feeling way, and how easy it is to extend an API by adding new types and fields. On the front end, clients are able to consume those types and fields in a flexible fashion. I enjoy the power the client has to use the API as it sees fit, rather than being subject to what the service thinks is important to include at a given endpoint. Part of my excitement for and enjoyment of GraphQL comes from the features of GraphQL itself, but like any technology, it is only as good as the tooling that surrounds and supports it. I see GraphQL's ability to reduce the friction between the server and client as one of its core strengths. So I'd like to demonstrate some tooling that plays to the strength of removing friction and show how GraphQL is uniquely positioned to enable this tooling. When put together, these tools make for what I find to be an incredibly delightful and productive developer experience. So I hope to leave you with some ideas for how you can take your GraphQL experience to the next level. The foundation of Salsify's GraphQL tooling is our shared conventions and guidelines that work to define what an idiomatic GraphQL schema looks like for us. To give a quick example of what I'm talking about, one convention we have is that an ID field should always return an ID type. A simple rule, but it helps make the schema predictable for anyone using it. Developing a consistent API is important, and these shared conventions not only make it easier to introduce new types in a consistent fashion without having to reinvent the wheel or go through the same discussion on pull requests, but also allow us to build convention-aware tooling. This convention-aware tooling helps avoid non-standard usage that might be confusing to other developers by flagging convention violations before the code ever leaves the developer's machine, and can help reduce boilerplate as we factor out common patterns. Now, I don't have time to go into exhaustive detail about all the GraphQL conventions we've developed at Salsify, but would like to highlight a handful of examples. First, we have a convention around how pagination should work. This includes how we name paginated types and the mechanics of the pagination. Next, we have conventions around how we expose the ability for clients to filter a collection of elements. These conventions manifest as a standardized filtering language. Along with filtering, we have conventions describing how to apply ordering to sorted fields in our graph. On the mutation side, we've established a handful of conventions that standardize how mutations are named, what their inputs look like, what their return types look like, and how errors are handled. Lastly, to avoid naming collisions around generic or common terms, we've developed a namespacing convention that helps tie types and fields to specific areas of the application. For example, we namespace types related to our application security by ensuring they have the security prefix. Before moving on from this discussion of conventions, I'd like to touch on when in the GraphQL adoption lifecycle you should start to think about establishing conventions and how you can start to develop and manage them. For the when, it is a trade-off between having enough real-world usage on the one hand and not wanting to delay too long to avoid building a large backlog of debt on the other. That said, developing your conventions upfront will generally be best to help ensure a consistent API. Furthermore, new scenarios will always emerge that your current set of conventions do not handle. So being proactive and establishing a convention for these emergent cases is also critical. Developing small working groups to go off and explore and prototype different solutions has proven to be an effective way to handle particularly complex scenarios. In terms of the how, at Salsify, we store our conventions in a GitHub repository so that changes go through a pull request process where any engineer can comment and flag concerns or propose alternatives. It is also important to build and engage internal GraphQL community within your organization, where different teams and their use cases are all represented. A Slack channel can be a useful tool for fostering this community by starting discussions and then flagging important pull requests for developers to review. These conventions and our convention-aware tools span the full stack of development, from schema definition on the back end to API consumption on the front end. Since it is the full suite of these tools that create the cohesive developer experience, I'd like to paint the full picture of this tooling for you, starting on the back end with Schema Generation. At Salsify, we never write in the GraphQL schema definition language, or SDL, by hand, as the SDL lacks some of the nice ergonomics a schema author might want. To help foster a better authoring experience, we use a Ruby DSL that generates the final GraphQL schema. Our Ruby DSL is a wrapper around an open source GraphQL Ruby gem we have extended to incorporate the previously mentioned conventions. Since Ruby is a language Salsify's engineers are already comfortable with, the DSL makes it easy to introduce new types to the schema quickly or define a proof of concept to share with others. The DSL aims to make it easier for developers who may be unfamiliar with GraphQL to quickly ramp up and start contributing, as they don't have to learn the GraphQL SDL to get started. Furthermore, as I mentioned at the start, another major benefit of our convention-aware schema generation is how it helps reduce boilerplate. So I want to show what that looks like in practice with a few of our standardized patterns. This is what it looks like to define a GraphQL type in our Ruby DSL. This is where we'd be able to detect and flag convention violations. For example, if I gave this ID field the wrong type, I'd get an error when trying to generate the schema. This paginated field helper makes it easy to avoid repeating all the boilerplate that comes from implementing a paginated field in accordance with our conventions. You can see in the generated SDL how that single paginated field statement expands into a bunch of automatically generated types. This ability to avoid having to manually type out repeated patterns is one of the major benefits of the Ruby DSL, as the GraphQL SDL isn't optimized for authoring, as it requires a lot of duplication. For example, an interface in the SDL requires that you duplicate fields between the interface and the implementing types. That results in a lot of duplicate code. We can see this in action with a helper we have for generating types for asynchronous operations, such as long-running jobs that go through multiple states. On the left, we have a Ruby DSL that defines each state that a job can be in, and then on the right, we have the GraphQL types that represent the generic job interface and each state. In this simple example, we have a running state that indicates some amount of progress, which is reflected by the running published blog post job type on the right. Next, we have a terminal failed state that reports failure reason. And lastly, a terminal completed state that contains the resulting payload of the job. You can see we never need to repeat fields in the Ruby DSL like we did in the GraphQL SDL. Now, you don't have to use Ruby specifically or this particular library, as there are libraries for other languages you could write similar tools in. But that said, we found Ruby's expressiveness makes for a great experience, especially when paired with the awesome open source GraphQL Ruby library. Hopefully I've shown how easy it is to flesh out even a complex schema with a few lines of Ruby. Even though the API does not work yet, with a schema defined, front-end developers can start building based off those new GraphQL types, while the back-end developers make sure the API actually works. This ability to parallelize work once the team has defined the schema helps accelerate development and reduces friction within the team, as both front-end and back-end developers can work off the shared contract that is the GraphQL schema. With that in mind, I'd like to transition to talking about some of the tooling that helps supercharge our front-end development, starting with schema management. Like many, we at Salsify are excited about the promise of federation and having a single unified graph. But in practice, we are still working to get there. As a result, a front-end project may have to manage individual schemas from multiple microservices. Tooling again comes to the rescue here, as we offer developers a straightforward process for configuring, fetching, and managing schemas from multiple microservices within a single project. This is a look at the configuration for pulling a single services schema into a client-side project. We'd be able to repeat this configuration for as many services as the client needs to communicate with, but we'll focus on three major blocks that make up this configuration. First, this section defines a mapping between the GraphQL documents and the schema they belong to. This powers generic toolers like linters and IDE extensions. You can see how we use a standardized pattern to help indicate which schema a document corresponds to via the file name. So rather than having to enumerate every document and keep that list of documents up to date, we can just use this simple pattern that we include the .demo suffix in the file name. The second block of configuration defines where this gets where to fetch the schema from and where to save it. So we have the service's GraphQL endpoint and a file path to save the dumped SDL to. This last section is the most complicated, as it allows us to automatically generate TypeScript types from our GraphQL schema and documents. We're able to hide most of the complexity behind this build generates config function that wraps some open source plugins, and this allows us to ensure that they work well with our conventions and other tooling. This ability to generate TypeScript types is a core piece of the great development experience for our front-end developers, so I'd like to dive deeper into it. One of the major benefits of GraphQL is the type information that the schema carries. We know the exact shape of the data based on the schema and the query we are making. More importantly, our machines can understand this type of information, which we can leverage in our tooling. At Salsify, we found the type information carried by GraphQL makes it a perfect companion for TypeScript, as TypeScript allows us to make use of that type information in our JavaScript code. Good tooling is again critical here, as the TypeScript types are worthless if they do not accurately reflect the GraphQL schema or the query we are making. For example, if I remove a field from my query but forget to remove it from the type definition, then we lose many of the benefits of type checking. The solution is to automate it to reduce the risk of human error. I'm going to jump to my IDE now so I can show what this looks like live. So here I'm working on this piece of code where we're looking to get a list of blog post titles given some query string. I've already written up a GraphQL client for our demo service, and I've written a function that will leverage that client to make a blog post search query. So I want to jump over to look at what the blog post search query looks like. So you can see I have a skeleton of it already. So right now I'm just fetching the ID. And on the right here, you can see the automatically generated types that I've been talking about. So here we have the ID string that we're pulling from the query. So I'm going to need to add some additional fields to this query. So I'm going to pull in the title, the body of the post. I'd also like to get the author and their email. So now when I save this, you can see that on the right, the types will automatically update. So now I have along with the ID, I have the title, which is a string, the body, which is string, and the author, it knows that it has this nested email field. So now I can jump back over to my code here and implement this function. So I'm going to have to map over the posts. And this is where the power of these automatically generated types gets really cool. You can see my IDE tells me exactly what's available as I'm typing it out. So I have the author, the body, the ID, and the title. And if I chose something like the author, it tells me I have the email. So even though I'm unable to see my query anymore, I can still know exactly what's available based on what I've made my query be. So here I'm just going to take the title, and you can see that all type checks, that function all type checks. Now, if I went and say modified this query to either remove the title or maybe I want to alias it, like I think name is a better name for this field. So when my type regenerates on the right, you can see there's no longer a title field. And if I jump back, you can see now the type checking fails. So it's telling me that title no longer exists, and I would have to replace it with something like name. So this quick feedback loop where you can instantly see any errors helps increase our confidence in our code and allows us to detect changes early on rather than letting them get to production. So I'm going to change this back to title. Now let's say I wanted to refactor this a bit and pull this out into a format post title function. So I want to be able to pass a post into this function, but I don't know the type of this as it's one of the automatically generated types. But we can go ahead and write an alias type. So I'm going to write a blog post type. And we've written this dig helper type that allows us to dig into one of our automatically generated types. So here I'm going to take the blog post query, and now I just need to specify the type or the path. So I need to go to the blog posts. Since it's paginated, I need to go to the entries and we'll just take a single entry. So now I can use this type in my function here. And you can see we get nice information about what is available on this blog post type, even though it's automatically generated. So even though it's decoupled from the even though it's or stays in sync with the automatically generated type. So if I go and added additional fields, I'd see them reflected here. So even if this is in a totally different part of my code base, I can still see exactly what's available based on the query that I made. So in this case, I'm going to write this function here. So I want to pull off the post of the title, or the title of the post. And let's say I also want to include the author's email. So I'll grab the author and their email. Cool, so now everything type checks, and I can go ahead and use this new function in my code here. And again, you can see everything type checks, so we have some confidence that our code's going to work as expected, and if we broke something, the type checker would let us know. And then the last thing I want to show you is we can, again, rely on our conventions to reduce this type a little bit. So I want to write a second version of this type where I use a paginated entry helper type that we've written. So now I don't need to write out all that extra boilerplate. So you can see this type works the same, everything still type checks, and we get the same nice information about what's available. So hopefully that shows just how cool these automatically generated types are and how powerful they are for creating a great developer experience and for reducing errors within your code base as you're developing. So now we'll jump back to my slides and we'll talk about the next thing. So even with automatically generated types, we still want to be able to develop and test our front-end clients in a more integrated fashion, where we are actually making GraphQL requests. So this next section dives into our tooling for this end of the development journey, with a look at how we create a more realistic development environment with response mocking. So all the benefits we've seen so far around being able to decouple and reduce the friction between developing the client and the server are lost if we still have to spin up the server to generate responses during development or testing. So one option would be to stub the server's responses. But since there are so many different ways to traverse this graph, trying to manually stub the backend responses and then keep those stubbed responses up to date would become incredibly burdensome. The solution we use at Salsify is an API mocking library called Mirage. By extending this tool with our own layer of default configuration, we have an easy way to set up Mirage to serve GraphQL requests. By again leaning into our conventions, we can make the out-of-the-box experience just work for most of the common use cases. Just create a Mirage model with the same name as a GraphQL type, and you get all the behaviors you would want for free. Things like lookup by ID, pagination, basic mutations, and errors all work with little to no configuration, as both our server and client are working off the same set of conventions. So the majority of our Mirage tooling is exposed through this make GraphQL Mirage handler, which handles the complexity of parsing and traversing incoming queries, loading records from the Mirage database, and then finally formatting the response correctly as a GraphQL response. While there are some additional points of configuration for supporting more complex behaviors or additional overrides when needed, you can see that developers need to specify very little configuration to get started. And they don't need to re-implement our common patterns and conventions, which helps further reduce the initial setup overhead and also reduces the risk of human error. So essentially, all we need to do is pass in the services schema that we set up earlier, and we're off and running. So the convention that makes our Mirage GraphQL handler just work is that we expect the GraphQL type and the Mirage model to have the same name. So in this case, we can create a blog post Mirage model to correspond to our blog post GraphQL type. When resolving nested GraphQL fields like the post title, our handler will know to just pull that field off the model. no extra configuration needed. This makes for a seamless development experience where the developer doesn't have to worry about manually setting up responses and then keeping those responses up to date as queries change. So we can see how straightforward this is with this example. So first, we're going to create an instance of our Mirage model to seed our mock server. So you can see here, I'm just creating a single blog post with a title. And now we can make our GraphQL requests, which Mirage will intercept and pass to the handler that we configured earlier. In this case, our blog post search query is accessing a paginated field. But again, due to the fact that this is convention-aware tooling, it's able to just work. And then lastly, you can see we get the result we'd expect. All of this without having to worry about what's going on at the GraphQL layer or the network layer. So hopefully this demonstrates how easy it is to develop, refactor, and test parts of your application that make GraphQL requests, all without having to worry about stubbing the responses. So up to this point, we've looked at the tooling that's going to help us build new features and how our conventions and the GraphQL schema allow the server and client to work off a shared contract. So for this last section, I'd like to show how we avoid breaking that contract and how we allow developers to safely and seamlessly evolve existing code in production, with a discussion of how we avoid breaking schema changes. While automatically generated TypeScript types based on the GraphQL schema help avoid bugs when developers write and modify their queries, there's still the danger that someone can make a breaking change on the backend. In this case, the client's type checking would not flag the issue until the developer pulled the latest version of the schema and regenerated the types. For example, let's say we change the blog post author field from non-nullable to nullable and then see what happens on the client side. Since the client still thinks that the author field will always be present, it blindly tries to pull the name without checking for null. This would be a safe assumption since the server would never be able to send a null author with the old schema. However, with the new schema, the client could run into an unexpected type error since the server is no longer bound by that non-null constraint. You can see we're just pulling the name here without checking for null, which could cause things to blow up. To defend against this danger, we've developed a build time check for the server that looks for and automatically flags any breaking changes to the GraphQL schema. We've instrumented our services to report which clients are using which fields, enum values, and arguments so that when this tool flags one of these breaking changes, we can either verify the change is safe because no one is using it, or know who we have to alert about the upcoming change. As a result, we have more confidence that we are not breaking things as we evolve our schema. I see this breaking change check as a good example of how the properties of GraphQL enable tooling that is not otherwise possible. For example, with a REST endpoint, the server doesn't know which pieces of the response a client is relying on, so changes to the response are all the more risky. With GraphQL, on the other hand, we know exactly which pieces of the API clients are using, down to the level of the individual fields. This ultimately helps us avoid breaking changes. So that wraps up the tools I wanted to show you. With that, I hope I demonstrated how these tools complement each other, allow the power of GraphQL to shine through, and create a delightful end-to-end user experience or developer experience. Furthermore, I hope there are some concrete ideas here you can take back to your teams for inspiration for your own tooling. GraphQL enables tooling that isn't possible with other technologies, so I urge you to lean into this benefit and strive to have tooling do the hard and tedious jobs while allowing developers to focus on the fun and impactful things like building new features. In the end, you'll have a safer, less error-prone system and a GraphQL experience that is more approachable, enjoyable, and productive. If this developer experience sounds awesome to you, come join us at Salsify. We're hiring. And with that, thank you for listening.